I want us to have a look at the hybridization of nitrogen in ammonia. All right, so we have in ammonia we have nitrogen, which is bonded to three hydrogen atoms, and it has a lone pair. Now, again, what you have to take note of is that the lone pair is also in an orbital. It is not in any open s orbital or p orbital. It is also in a hybrid orbital. So what do we need to account for the structure of nitrogen? So since the lone pair is also in an orbital, and we have three bonded pairs making a total of four, we need to have a hybridization that can give us four orbitals. So when you take nitrogen, which is the central atom, with atomic number 7, its configuration is 1s2, 2s2, 2px, 2py, and then we have 2pz. So each of these has one electron each. So in the 2s, we have a paired electron, and the p orbital, which is a degenerate orbital, we have three electrons, each in one in px, one in py, and one in pz. Okay. So again, when we take a look at the energy profile diagram, this is energy increasing. The 2s orbital has a pair of electrons, and the p orbital, which is of a higher energy, has three unpaired electrons. So this is the 2s orbital, and then the px orbital, py, and the pz. Okay. Now, what is going to happen is we'll have the 2s orbital mixing with the 2p orbitals to give us a hybrid orbital. Now, this hybrid orbital will all be of the same energy, and so we are going to have it around this region with four degenerate orbitals. That means they are of the same energy, and we are going to call it sp3 orbital because it's a combination of the s orbital and then three p orbitals. So remember, we have one of the orbitals with a paired electron and the rest with unpaired electrons. So this is our new hybrid orbital. Now, how is this going to bond with hydrogen and account for the structure of nitrogen? Now, normally for an sp3 hybridized orbital, it should have a geometry of tetrahedral. So we would be expecting that this new set of orbital will be around nitrogen in a fashion that will give us a tetrahedral geometry. All right. Now, one of the hybrid orbitals has a pair of electrons, while the others have one electron each. Now, the hydrogens which are they have only s orbital. They have only one electron, and they are three. So these three hydrogens will come and bond with the hybrid orbitals of nitrogen with their one electron each. And so they are going to form sigma bonds. So now, mind you, they can only bond with the orbitals with unpaired electron. because for this exclusion, the number of electrons that an orbital can take must be 2. So that is what gave us this structure, and we should be expecting a tetrahedral structure. But then that is not exactly what we are going to expect, because you'll notice that one of the hybrid orbitals has a pair of electrons. Now there's going to be a repulsion between the pair of electrons. So this is nitrogen. It's now having 3 hydrogens attached and a pair of electrons in a hybridized orbital. So this electron is going to try to push away the bonded pair, and in that way it's going to reduce the bond angle. And the bond angle is going to reduce from the normal 109.5 for a tetrahedral geometry to about 107. So as a result of that, nitrogen is going to have a geometry where we have the nitrogen with a hydrogen attached at one end, another one here, and then we have another one here. Now, when we trace this, we realize that it looks like it's having a base that is triangular, and then we have the electrons at the top of the nitrogen. So this geometry is what we call trigonal pyramidal. So nitrogen has trigonal pyramidal instead of the normal tetrahedral geometry of an sp3 hybridized orbital. So this is what accounts for the geometry in nitrogen. And notice that there's going to be a dipole moment because we have the nitrogen, which is much more electronegative than the hydrogens. And so we're going to have a dipole moment going. All right, so that is how we can account for the hybridization in nitrogen when we are talking about ammonia. Thank you.